Alright, in this video I'll be solving paper 32 for May-June 2024. So make sure to like the video, subscribe, and let's dive right in. Number 1, Part A. Sketch the graph of y equals modulus of x minus 2a, where a is a positive constant. Alright, so let's draw our Cartesian plane. So this here is our x-axis, this is our y-axis. Alright, so to sketch the graph of our modulus function, let's start by sketching the graph of its linear function. So we want to get the graph of y equals x minus 2a. We've been told that a is a positive constant, and so to be able to sketch the graph of this straight line, we need 2 points. So for example, we can evaluate this at x is 0. Our y coordinate should be negative 2a. So we're saying x is 0, so let's assume negative 2a is somewhere here. This is negative 2a. That's one of the points that our line passes through. And then we can do when y is 0. When y is 0, x must be equal to 2a. So when y is 0, x is 2a, that should be somewhere here. And then we're going to draw a line that passes through these 2 points. Okay, let me just shift that line downwards a little bit. I think that's better. Okay, so this here would be the equation of y is equal to x minus 2a. Now to get the modulus function from here, we simply have to reflect the part that's below the x-axis. So we have to reflect this part over here, right? So let's do that. So when we reflect the part that's below the x-axis, since here it intercepts the y-axis at negative 2a, on the positive y-axis it should intersect at positive 2a. So we're saying that this point here should be 2a. Okay, and then if we label our line here, that would be negative x minus 2a. And we've got the graph of our modulus function. And we should probably get rid of the part that's below the x-axis. So let me do that. So it should look like that. And this is the graph of our modulus function. Okay. Part B says solve the inequality 2x minus 3a is less than our modulus function from part A. So to see what's going on here, we can sketch the graph of y is equal to 2x minus 3a on the same Cartesian plane. Okay, again, this is a straight line, so we need 2 points that lie on the line. We know that when x is 0, our y value would be negative 3a. So I'll use a different color for that. So negative 3a would be somewhere here, negative 3a. And then we need another point that lies on this line. Let's do when x is equal to 2a. So when x is 2a, y is equal to 2 times 2a minus 3a. So y is 4a minus 3a, which is simply a. So we've got when x is 2a, we're saying our y value is at a, so it would be somewhere here, right here. And then we need to draw a line that passes through our 2 points. Alright, and this here is the line y is equal to 2x minus 3a. And you can tell that our line has a steeper gradient than our modulus function. And now we can tell that there's only one point of intersection, and that's between this equation from the modulus function and our line. So let's solve those two equations simultaneously for our point of intersection. Okay, so we've got y is equal to negative x minus 2a, and then we've got y is 2x minus 3a. So let's equate the two. That's negative x negative 2a is equal to 2x minus 3a. Let's expand the bracket. So negative x plus 2a is equal to 2x minus 3a. And now we want to make x the subject of the formula. So that's 2x plus x is equal to 2a plus 3a. So 3x is equal to 5a. Divide both sides by 3, x is equal to 5 over 3a. So what this means is that our point of intersection here is at 5 over 3a. And now we can look at our inequality. We want the region where our red line is below the blue line. So if we look at our graph here, we need to find the region where the red line is below the blue graph. So as you can tell, if we pick this point over here, we can tell that our red line is in fact below the blue line. And as we continue to go this side, our red line will always be below the blue line. But if you go beyond 5 over 3a, for example, at this point, our red line is now above the blue line. So it means that the region that we want is to the left of 5 over 3a. So we can conclude that therefore x is less than 5 over 3a, and that's our final answer. Number 2. Express 6x squared minus 9x minus 16 over 2x squared minus 5x minus 12 in partial fractions. Alright, so we've been given 6x squared minus 9x minus 16 over 2x squared minus 5x minus 12. Okay, so the highest power in the denominator is equal to the highest power in the numerator. This means we have an improper fraction. So use the method that you would usually use for decomposing into partial fractions when you have an improper fraction. So I'm not going to use long division because I prefer this method that I'm about to show you. So we've got our denominator, that's 2x squared minus 5x minus 12. Okay, and then we want to find a way to write our numerator in terms of our denominator. So I'm just going to put brackets here, and then we're going to write our denominator exactly as it is, 2x squared minus 5x minus 12. Alright, and now our goal is to make this numerator that we have here equal to the numerator we have on the left. So we start by looking at the coefficient of the term with the highest power. So in this case, that's the 6. So we need to find a number we can multiply the bracket by to get that 6. So if we multiply by 3 here, when we expand, 3 times 2x squared does in fact give us a 6x squared. Alright, so that's the first step. But notice how this 3 then affects all the other terms, because 3 times negative 5x gives us negative 15x, which is not equal to what we have here, and 3 times negative 12 does not give us negative 16. So we're going to have to fix that by adding or subtracting outside of the bracket. So we say 3 times negative 5x will give us a negative 15x, but we want to get negative 9x. So it means we have to add 6x to get our negative 9x. So it means outside the bracket here, we add 6x. Okay, and then for the term independent of x, we've got 3 times negative 12, that's negative 36, and we want to get a negative 16. So to do that, we need to add 20. So we'll do that outside the bracket, we add a 20. Because the idea is if we are to simplify what we have right here, it should equal what we have here. So we can check on the side, 3 times 2x squared minus 5x minus 12 plus 6x plus 20. If you expand that, that's 6x squared minus 15x minus 36 plus 6x plus 20. So we've got 6x squared, then minus 15x plus 6x, which gives us minus 9x, minus 36 plus 20, which gives us minus 16. And this is exactly the same as this numerator over here. Okay, But the main reason we did it this way is so that we can distribute our denominator and write this as 3 times 2x squared minus 5x minus 12, and then you stop at the end of the bracket and you give it the denominator, which is 2x squared minus 5x minus 12, or basically splitting it at this point, right? So that's plus 6x plus 20, and again you also give it the denominator 2x squared minus 5x minus 12. Okay, so here on the left we can cancel out and we end up with 3 plus 6x plus 20 over 2x squared minus 5x minus 12. So the goal of this was just to get this constant, and so that we can end up with a fraction that is proper. Alternatively, you can use long division if you prefer that. Alright, so now we can go on to decompose this proper fraction into partial fractions. So we've got 6x plus 20 over 2x squared minus 5x minus 12. In fact, we should probably factorize this first into its linear factors. So that's 2x and then x here. So we can do a negative 4 here plus 3. 2 times negative 4, that gives us negative 8, plus 3, that gives us negative 5. Yes, that's correct. Okay, and so we can say a over 2x plus 3, since we've got a linear factor. And for the second one, it's also linear, so it's b over x minus 4. And now we want to get rid of all the denominators, so we multiply through by 2x plus 3 times x minus 4. So that's 6x plus 20 is equal to a times x minus 4 plus b times 2x plus 3. Okay, so now let's start by evaluating. Let's evaluate b first. So let x equals 4, because if you substitute x with 4 here, this becomes a 0, and that allows us to evaluate b. So that 6 times 4 plus 20 is equal to b times 2 times 4 plus 3. So 6 times 4 is 24 plus 20, that's 44. And then we've got 8 plus 3, so that's 11b. And this means that our b must be equal to 4. Alright, and now we can say let x equal, that is negative 3 over 2, negative 3 over 2, because 2x plus 3, if you substitute it with negative 3 over 2 here, the 2's cancel out and you end up with negative 3 plus 3 equals 0, making this bracket over here 0 and allowing us to evaluate a. So that means we've got 6 times negative 3 over 2 plus 20 is equal to a times negative 3 over 2, negative 4. Alright, so let's simplify. Our left hand side is 6 times negative 3 over 2 plus 20, and that gives us 11. And this is equal to, that's negative 3 over 2 minus 4, so negative 11 over 2a. So let's multiply both sides by negative 2 over 11 times negative 2 over 11. So that means that our a here would be, this would cancel out and you get negative 2. Alright, do we still have space below? No, we don't have space. So on the side we are going to conclude that therefore, had they defined it as f of x? No, they had not. So let's just write the whole thing, 6x squared minus 9x minus 16. Therefore 6x squared minus 9x minus 16, and this is being divided by 2x squared minus 5x minus 12, and this is equal to, don't forget that we've got this constant that we evaluated first, And then what we found here when we're looking for a and b are the partial fractions of this. So don't forget to start by writing the 3 first and then your partial fractions. So it's going to be 3 plus a is minus 2, so minus 2 over, that's 2x plus 3, 2x plus 3, plus b, which is 4, so plus 4 over x minus 4, x minus 4. And this here would be our final answer. Number 3, the variables x and y satisfy the equation a to the power 2y minus 1 is equal to b to the power x minus y, where a and b are constants. Part A, show that the graph of y against x is a straight line. So we can use logarithms to reduce this to a linear form. So we've got a to the power 2y minus 1 is equal to b to the power x minus y. So we can say ln a to the 2y minus 1 is equal to ln b to the power x minus y. And using laws of logarithms, particularly the one that says ln a to the n is equal to n ln a, we can simplify this to become 2y minus 1 times ln a. So this basically allows us to bring down the power. Okay, and we can do it on the other side as well. So that's x minus y ln b. Okay, and then let's expand our brackets. So 2y times ln a, 2y ln a, minus 1 times ln a, so minus ln a is equal to x times ln b, x ln b, minus y times ln b, minus y ln b. Okay, we want a graph of y against x, so we need to make y the subject of the formula. So let's put everything that has y on one side, so that's 2y ln a, and then we'll bring the negative y ln b that side, so it becomes positive y ln b, and this is equal to, we've got our x ln b, and then we're taking negative ln a that side, so it becomes positive ln a. Okay, and now let's factor out the y, so this becomes y 2 ln a plus ln b is equal to x ln b plus ln a. And then for the 2 ln a here, we can use this law of logarithm but in reverse. So 2 ln a becomes ln a squared, so that's y times ln a squared plus ln b is equal to x ln b plus ln a. And then at this point we are going to use the law of logarithms that says ln a plus ln b can be written as ln a times b. Okay, so in our case we end up with y ln a squared times b, and this is equal to x ln b plus ln a. Alright, now let's continue on the side. We've run out of space, so let's make y the subject of the formula. Y is equal to, that's ln b divided by ln a squared b. Alright, and then we've got our x here plus ln a over ln a squared b, And now this is pretty much the same as the form y is equal to mx plus c, because this here represents the m, and then this here represents our y-intercept, and then y matches y, x matches x. So we have reduced it to the equation of a straight line. Part B. Given that a is equal to b cubed, state the equation of the straight line in the form y is equal to px plus q, where p and q are rational numbers in their simplest form. Alright, so we have our equation to be y is ln b over ln a squared b, x plus ln a over ln a squared b. And we've been told that a is b cubed. So wherever we've got an a, we're going to replace it with b cubed. So ln b over ln, there is a squared, so a squared would be b to the 6. So this is b to the 6 times b, alright, x plus ln a is b cubed, so ln b cubed, over, this is the same as this, so ln b, that's ln b to the 7. Okay, so let's just simplify everything. We've got y is ln b over ln b to the 7 x plus ln b cubed over ln b to the 7. Alright, so now at this point we are going to use the law of logarithms that says ln a to the n is equal to n ln a. So we're going to use it here, here, and here. So let's do that. That's y is equal to, that's ln b over 7 ln b x plus, that's 3 ln b over 7 ln b. And this allows us to cancel. So here we can cancel the ln b, so that is y is equal to 1 over 7x, and likewise we can cancel ln b here, and that's plus 3 over 7. And we've been told that p and q are rational numbers, so we can leave it exactly like this, and that's our final answer. The equation of a curve is y to the 2x plus y squared ex is equal to 6. Find the gradient of the curve at the point where y is equal to 1. Alright, so the gradient here refers to dy dx. So that's what we have to find. And we can tell that the function that we have is implicit, because there's no easy way to make y subject of the formula. So let's differentiate it implicitly. So this is y to the 2x plus y squared to the x is equal to 6. So here, so for the first part we've got a product, so I'm just going to hold the y and then I'll differentiate to the 2x. So if we differentiate that, that becomes 2e to the 2x plus, now we're going to hold the to the 2x and then differentiate y. If you differentiate y, you get dy dx. Okay, and then here we've got another product. So again, I'm going to hold y squared and then differentiate to the x. If you differentiate to the x, you get to the x. And then now I'm going to hold the to the x and then differentiate y squared. If you differentiate y squared, you get 2y. Let me put a multiplication sign here. 2y dy dx. Alright, and this is equal to, if you differentiate a constant, you get 0. Alright, so let's simplify what we have. We've got, that's 2y to the 2x plus to the 2x dy dx plus y squared to the x plus 2y to the x dy dx. And now our goal is to make dy dx subject of the formula. So we're going to move everything that doesn't have dy dx to the right hand side, so that on the left we remain with to the 2x dy dx, which is this part over here, plus 2y to the x dy dx, which is this part, and then everything else is moving right. So we've got negative y to the 2x, that's here. Then we've got negative y squared to the x. Alright, and now we want to make dy dx subject of the formula, so we're going to factor it out. So that's to the 2x plus 2y to the x, and this is equal to negative 2y to the 2x minus y squared to the x. So dy dx is equal to negative 2y to the 2x negative y squared e to the x, and this is all over e to the 2x plus that's 2y e to the x. And we can even go ahead and simplify this by factoring out an e to the x in both the numerator and the denominator, but I'm not going to do that because it's not necessary. We want to find the gradient of the curve at the point where y is 1. Okay, so to do that, we first need to evaluate our x coordinate when y is 1. So let's substitute y is 1 into our original equation. We end up with e to the 2x plus e to the x, and this is equal to 6. So moving everything to the same side, that's e to the 2x plus e to the x minus 6, and this is equal to 0. Okay, and so this is a hidden quadratic because this here can be written as e to the x squared plus e to the x minus 6. This is equal to 0. So let's factorize this. That's e to the x. 1 factors of negative 6 that add up to 1. So that would be, we can do positive 3 and a negative 2. 3 minus 2 gives us 1. So that means our e to the x can be either 2 or e to the x can be negative 3. So let's apply the natural logarithm to solve for x. So this becomes x is equal to ln 2, and in this case, if we apply the natural logarithm, we get an error because we know that our natural logarithm does not take values of x that are negative. So here x is no, let me just scroll here so that it's clear, it's no solutions. Okay, so it means the x value that we're taking here is x is ln 2. So we're saying when y is 1, our x is ln 2. So we can substitute that into dy dx here. So negative 2 times y, which is 1, and that's e to the power 2 times our x. Our x is ln 2. So this becomes ln 2 minus our y squared, so 1 squared, and this is e to the ln 2, and this is all over. On second thought, we probably should factor out that exponential that I said doesn't matter. Okay, so let's do that. In our numerator for dy dx, let's factor out our exponential. So the exponential of x, we end up with negative 2y, that's e to the x, minus y squared, and this is over. We'll do the same in the denominator, factor out e to the x. We end up with e to the x plus 2y. So that would then cancel out. So dy dx is equal to, that's negative 2y e to the x minus y squared over, that's e to the x plus 2y. It would just make our calculation a lot simpler given that we're dealing with x is ln 2. So that's why it's probably best to factor out that exponential. Anyway, so this becomes negative 2 times y, which is 1, times e to the x, x is ln 2, minus y squared, so that's minus 1 squared, and this is over, that's e to the x, so e to the ln 2 plus 2 times y, so times 1. Our numerator here is negative 2 times, the e and the ln will cancel out, and we end up with the 2, and that's minus 1 over our denominator, e and ln cancel out here, so you've got 2 plus 2, and this leads to, that's negative 4, negative 1, so negative 5 over 2 plus 2, which is 4. So we can conclude that therefore the gradient dy dx is equal to negative 5 over 4, and that's our final answer. Number 5, part A. It is given that the equation e to the 2x is equal to 5 plus cos 3x has only one root. Show by calculation that this root lies in the interval x is between 0.7 and 0.8. Okay, so what we can do is we're going to move all the terms onto one side, and we're going to call this function f of x. So f of x is e to the 2x minus 5 minus cos 3x. And then we're going to evaluate f of 0.7 and f of 0.8. And if we have a change in sign, it means a root must lie between these two values. So f of 0.7 is e to the 2 times 0.7 minus 5 minus cos 3 times 0.7. So let's punch that into the calculator. That's e to the power 2 times 0.7 minus 5 minus cos 3 times 0.7, and that gives us, that's negative 0.43995, and so on. Alright, let's do the same for 0.8. So f of 0.8 is e to the power 2 times 0.8 minus 5 minus cos 3 times 0.8 is equal to, let's punch that into the calculator, e to the power 2 times 0.8 minus 5 minus cos of 3 times 0.8, and this gives us a positive 0.6904, and so on. Alright, so since we have a change in sign, we can conclude that since there is a change in sign, because this here is negative and this is positive, a change in sign that looks like plus or minus now. A change in sign, this root that we're talking about, this root lies in the interval, or in the interval 0.7 and 0.8. Part B says that show that if a sequence of values in the interval x is between 0.7 and 0.8 given by the iterative formula xn plus 1 is equal to half ln 5 plus cos 3x to the n converges, then it converges to the root of the equation in part A. Okay, so I'm just going to rewrite this without the n and n plus 1. So x is equal to half ln 5 plus cos 3x. So basically what they want us to do is to just simply prove that this equation here is the same as this equation here. And what we can do is to try to identify which x has been made the subject of the formula in this equation that we have here. So this ln here tells us that the x that has been made subject of the formula must have come from an exponential. So it means it's this x that has been made subject of the formula. So let's work with our initial equation, this one, to show that it can be written as this second equation. So we've got e to the power 2x is equal to 5 plus cos 3x. Alright, and now we want to apply the natural logarithm to both sides. So 2x is equal to ln 5 plus cos 3x. And then we can multiply both sides by half. So x is equal to 1 over 2 ln 5 plus cos 3x. So it does indeed converge to the root of the equation in part A, since we have shown that this equation is the same as that equation. Alright, part C says use this iterative formula to determine the root correct to 3 decimal places. Give the result of each iteration to 5 decimal places. Alright, so our iterative formula is xn plus 1 is equal to half ln 5 plus cos 3, that's x to the n. So we need an initial value which I'll call x0. We can use let's see, let's use 0.7. This 0.7, yeah, we can use that as our initial value, 0.7. So it means x1 is equal to half ln 5 plus cos 3 times our x0, which is 0.7. Let's punch that into the calculator. 1 over 2 ln 5 plus cos 3 times 0.7. That gives us 0.75. We want the result of each iteration to 5 decimal places. So 1, 4, or 5 decimal places, that would be 50, because that's 4999. So 50. Okay, and then we go on to the second iteration. That's half ln 5 plus cos, that's 3. I'll replace the 0.7 with ans, which is the button next to your equal sign. On most calculators it's written ANS, right? And that just basically stores the answer from the previous calculation. So let's do that. Replace 0.7 with ans and press equals. You should get the result of our second iteration, so 0.73719. Okay, let's go on to the third iteration. Don't change anything on your calculator. Since ans is storing the value of our previous iteration, we can press equals. So that's 0.74105. They want the answer to 3 decimal places. Okay, I thought we had our answer, so let's keep going. So press equals again, don't change anything. This is 0.73. Oh my, that is 74000. Okay, and then we go on to the next iteration. We're not quite there yet. Press equals. This is 0.74028. 1, 2, 3, 4, 5. Okay, so we have arrived at our answer. It's 0.740. And we can conclude that therefore x is equal to 0.740, and that's our final answer. Number 6. The diagram shows the curve y equals xe to the negative ax, where a is a positive constant and its maximum point m. Part A. Find the exact coordinates of m. So m is a stationary point, which means that if we want its coordinates, we first have to find dy dx. Okay, so dy dx would be, we've got a product here, so let's hold the x, then differentiate e to the negative ax, so that would give us negative a e to the negative ax. Alright, and now I'm going to hold the e to the negative ax, then differentiate x, you get 1. So it means our dy dx is equal to negative ax e to the negative ax plus e to the negative ax. And we can factor out e to the negative ax, so that this becomes e to the negative ax times negative ax plus 1. Alright, and now we can equate this to 0. So e to the negative ax, since we're solving for a stationary point, this is equal to 0. Equate each expression to 0. So e to the negative ax is 0, and then we've got negative ax plus 1 is 0. Alright, so here to get rid of our exponential function, we have to apply the natural logarithm to both sides, but if we do that, we end up with an error because the natural logarithm cannot take values of x that are less than or equal to 0. Okay, so it means our solution must come from this equation over here. This becomes ax is equal to 1. So divide both sides by a to make x subject of the formula. X is 1 over a. Now we need to find the y coordinate. So we've got y is equal to x e to the negative ax. So this becomes y is equal to, wherever there's an x, we're substituting with 1 over a. So that's e to the negative a times 1 over a. So y is equal to, that's 1 over a. This here will cancel out, and so we end up with e to the negative 1. So we can write this as y is equal to 1 over ea or ae. Let's write it as ae. Okay. So therefore the coordinates of m are x is 1 over a and y is 1 over ae. And this here is our final answer. Part B. Find the exact value of the integral from 0 to 2 over a of x e to the negative ax with respect to x. So we are integrating our product. So let u equal x, and then our dv dx will be the exponential, because u in this case we're using late, right? Where the e here would be our exponentials, and then our a here is the algebra. So your algebra is your x squared, that's your algebra. So it means that L would be logarithms, and T is trig. So in this case it means our u will be x. So you pick your u depending on how high the function is on this list. In this case, the highest function that we have is this algebraic function, the x, right? So that becomes our u, and our exponential is at the very bottom, so we're not going to pick that as our u. Anyways, so our dv dx is e to the negative ax. Let's find du dx. Du dx here would be 1, and then our v is, that is negative 1 over a e to the negative ax. Alright, so we can write this as the integral. I'm going to ignore our limits for now, of x e to the negative ax with respect to x is equal to uv. So that's negative 1 over ax e to the negative ax minus the integral of v du. So 1 times negative 1 over a e to the negative ax. Alright, with respect to x. So let's focus on this integral. Let's work on it on the side. So this is the integral of, that's negative 1 over a e to the negative ax with respect to x. So I believe a is a constant, right? It has to be, otherwise, yeah, a is a positive constant. Okay, so we can take the negative 1 over a outside our integral sign. Negative 1 over a, the integral of e to the negative ax with respect to x. And now we know that if we integrate e to the negative ax, we get negative 1 over a e to the negative ax. So this becomes negative 1 over a times negative 1 over a e to the negative ax, which is 1 over a squared e to the negative ax. So we can substitute this integral here with this result. So it means we've got the integral x e to the negative ax with respect to x is equal to negative 1 over ax e to the negative ax. Be careful, don't forget that we had the minus sign outside of our integral. So this is multiplying our 1 over a squared e to the negative ax. In fact, let me just get rid of that bracket. Since it's one term, it will not matter. Alright, and we can even go ahead to factor out negative 1 over a squared e to the negative ax. So just factoring out this whole thing together with its negative sign. So this becomes, that is ax plus, because remember we've also factored out the negative sign, so plus 1. And now we're going to bring back our limits. So that's 0 to 2 over a, 0 to 2 over a. And now we can go ahead and substitute in our limits. So we'll start with our upper limit, negative 1 over a squared e to the negative a times 2 over a. We've got a times 2 over a plus 1. So that is our upper limit. Now we go on to our lower limit. That's negative 1 over a squared. Then we've got e to the negative. We're going to substitute this x with a 0, so it ends up being e to the power negative 0, which would be a 1. Okay. And then we've got a times x, so that's a times 0, which would be 0 here. And then we've got the plus 1, so that's another 1. Okay, so let's simplify. Here we're going to get negative 1 over a squared, and then e to the negative, the a's cancel out, so that's e to the negative 2. And then here the a's cancel out again, so you end up with 2 plus 1, which is 3, minus our lower limit. That would give us negative 1 over a squared. Alright, so let's simplify. What do we have here? We've got negative 3 over a squared e to the negative 2 minus minus, so positive 1 over a squared. So we can go ahead and factor out 1 over a squared, or we could just leave it as it is, but I think it's a bit cleaner if we factor out the 1 over a squared. So that's negative 3e to the negative 2 plus 1, and this here is our final answer. Number 7, part A. Show that cos to the 4 theta minus sine to the 4 theta is identical to cos 2 theta. Okay, so let's work from the left hand side to the right hand side. So we've got cos to the 4 theta minus sine to the 4 theta. And this is actually a difference of 2 squares. We know that anything in the form a squared minus b squared can be written as a minus b times a plus b. So this here is basically, that's cos squared theta squared minus sine squared theta squared. So the cos squared theta is basically our a, and then the sine squared theta is b. So that means we can write this as cos squared theta minus sine squared theta times cos squared theta plus sine squared theta. And what we can now do here is to use the identity sine squared theta plus cos squared theta is identical to 1 to replace this bracket, because we know that cos squared theta plus sine squared theta is the same as 1. So this becomes cos squared theta minus sine squared theta multiplied by 1. And this is cos squared theta minus sine squared theta. And we know that this is in fact identical to cos 2 theta. And we have proved their identity. Part B. Hence find the exact value of the integral from negative 1 over 8 pi to 1 over 8 pi of cos to the 4 theta minus sine to the 4 theta plus 4 sine squared theta cos squared theta d theta. Alright, so from part A, we know that this here is equal to cos 2 theta. Alright, and now this here actually looks familiar. I'm going to just bring it here to the side. This is 4 sine squared theta cos squared theta. And we can actually write this as 2 squared sine squared theta cos squared theta. And if we sort of factor out the power 2, what we have is 2 sine theta cos theta, and this is all squared. Now you should know that we've got a double angle for this expression that we have in the bracket in sine 2 theta. So sine 2 theta is identical to 2 sine theta cos theta. So it means that that can be written as sine 2 theta squared. Alright. And so we can come back here and we're going to replace that with sine 2 theta squared, and we can go ahead and carry out our integration. So this is the integral from negative 1 over 8 pi to 1 over 8 pi of, that is cos 2 theta plus our sine 2 theta squared, and I'm going to put a big bracket here. This is all with respect to theta. Even though we have simplified the above expression, we still can't integrate this with ease. So we need to simplify this further. And to help us, we are going to use the identity or the double angle formula for cos 2 theta, where it's equal to 1 minus 2 sine squared theta. So I want you to notice how when we have 2 theta here, on the right hand side we've got half that angle, so we've got theta. So it means that if we had cos 4 theta, our identity would be 1 minus 2 sine squared 2 theta. And if we had cos a theta, our identity here would be 1 minus 2 sine squared 4 theta. But in this case, the one we want is for 4 theta. Alright, so in this identity here, I want to make sine squared 2 theta the subject of the formula. So this becomes 2 sine squared 2 theta is equal to 1 minus cos 4 theta. And let's divide both sides by 2. So sine squared 2 theta is equal to half minus half cos 4 theta. Alright, so what this means is that we can substitute our sine squared 2 theta with half minus half cos 4 theta. And so this becomes the integral from negative 1 over 8 pi to 1 over 8 pi of that cos 2 theta plus 1 over 2 minus 1 over 2 cos 4 theta, and this is all with respect to theta. And now we can finally integrate. So if you integrate cos 2 theta, you're going to get 1 over 2 sine 2 theta plus, if you integrate a half, you're going to get half theta minus, that's half. If you integrate cos 4 theta, you get 1 over 4 sine 4 theta. And our limits are from negative 1 over 8 pi to 1 over 8 pi. Let's simplify this first. That's 1 over 2 sine 2 theta plus 1 over 2 theta minus, this becomes 1 over 8 sine to the 4 theta. From negative 1 over 8 pi to 1 over 8 pi. And let's substitute in our limits. So we'll start with our upper limit. So that is half sine 2 times 1 over 8 pi plus half times 1 over 8 pi minus 1 over 8 sine 4 times 1 over 8 pi. Okay, it looks like we're going to run out of space, so I'll put the lower limit here. So that's half sine 2 times negative 1 over 8 pi plus half times negative 1 over 8 pi minus 1 over 8 sine 4 times negative 1 over 8 pi. Alright, be careful with the brackets, they are a lot. And now let's simplify. So we'll start with the upper limit. We'll start with this bit over here. So let's punch that into the calculator. That's 1 over 2 sine 1 over 4 pi. That gives us root 2 over 4. Root 2 over 4. Then we move on to 1 over 2 times 1 over 8 pi. That's positive 1 over 16 pi. Then we've got negative 1 over 8 sine, that's 1 over 2 pi, and that gives us a negative 1 over 8. And now let's move on to the lower limit. So that's half sine, that's negative 1 over 4 pi, and this here, this part gives us negative root 2 over 4. Okay, then we've got half times negative 1 over 8 pi, so that's negative 1 over 16 pi. Okay, and now let's move on to this last part. So that's negative 1 over 8 sine negative 1 over 2 pi, and that gives us, that's a positive 1 over 8. So let's simplify now. We've got root 2 over 4 plus 1 over 16 pi minus 1 over 8. Let's expand our bracket. So that's positive root 2 over 4, positive 1 over 16 pi minus 1 over 8. Okay, so root 2 over 4 plus root 2 over 4 gives us, that's root 2 over 2. Then 1 over 16 pi plus 1 over 16 pi, that's 2 over 16 pi, so 1 over 8 pi. And then minus 1 over 8 minus 1 over 8, that's minus 2 over 8, so minus a quarter. And this here is our final answer. Question number 8. The points A, B, and C have position vectors. OA is equal to negative 2i plus j plus 4k. OB is 5i plus 2j, and OC is 8i plus 5j minus 3k, where O is the origin. The line L1 passes through B and C. Part A, find a vector equation for L1. Alright, so we're told that L1 passes through B and C. So the first thing that we need to do is to find the direction vector of L1, which would be BC. So BC would be OC minus OB. Okay, so our BC would be, our OC is 8, 5 minus 3, 8, 5 minus 3, minus OB, which is 520. 520 looks like a 6, that should be a 0, and this gives us 8 minus 5, which is 3, 5 minus 2, which is also 3, minus 3 minus 0, which is minus 3. So we can say that therefore the equation for L1 is R is equal to, we need a point on the line, so we can use OB, which is 520, plus lambda, that's our direction vector, BC, 3, 3, negative 3, 3, 3, negative 3, and this is our final answer. The line L2 has equation R is equal to negative 2i plus j plus 4k plus mu 3i plus j minus 2k. Part B, find the coordinates of the point of intersection of L1 and L2. Alright, so L1 has the equation 520 plus lambda 3, 3, negative 3, and then L2 has the equation that's negative 214, negative 214, plus mu, that's 3, 1, negative 2, 3, 1, negative 2. Okay, So we're told that these two lines intersect and we need to find the coordinates of their point of intersection. So to find the coordinates of the point of intersection, we have to solve simultaneously. So from the equation of line L1, we can get 5 plus 3 lambda, and this should be equal to negative 2 plus 3 mu, negative 2 plus 3 mu, and we could also get 2 plus 3 lambda, 2 plus 3 lambda, and this should be equal to 1 plus mu, 1 plus mu, and we can also get a third equation, which is 0 minus 3 lambda, so minus 3 lambda is equal to 4 minus 2 mu, 4 minus 2 mu. Alright, so I'm going to use our second equation to make mu the subject of the formula. So we've got 2 plus 3 lambda is equal to 1 plus mu. So mu should be equal to, that's 2 minus 1 plus 3 lambda. Mu is equal to 1 plus 3 lambda. We can go ahead and substitute mu equals 1 plus 3 lambda into the third equation, and this allows us to evaluate lambda. So negative 3 lambda is equal to 4 minus 2 mu. We said mu is 1 plus 3 lambda. So now we want to solve for lambda. So negative 3 lambda is equal to 4 minus 2 minus 6 lambda. So negative 3 lambda is equal to, that's 2 minus 6 lambda. And so now let's solve for lambda. We get 3 lambda is 2, which means that lambda is equal to 2 over 3. So the picture that we have here is we've got a line L1 that is intersecting a line L2. So let's say this is L1 and this is L2, and we're looking for the point of intersection. We've found that at this point of intersection, lambda must be equal to 2 over 3. So using the equation for L1, we know that any general point is of the form 5 plus 3 lambda. So 5 plus 3 lambda, basically just this side here. This gives us the coordinates for x, y, and z, like this. These are the general coordinates for any point that lies on the line. So this here is 2 plus 3 lambda, and that's minus 3 lambda. So when we want to find a specific point on that line, we then have to evaluate the lambda for that point. And we know that for our point of intersection, lambda must be equal to 2 over 3. So to get the coordinates of the point of intersection, we simply substitute our lambda. So this here becomes that 5 plus 3 times 2/3, 2 plus 3 times 2/3, minus 3 times 2/3. Alright, and so that simplifies to give us, that's 7, and then that's 4, and that there is a 2, negative 2 rather, negative 2. These are the coordinates for the point of intersection. Part C, the point D on L2 is such that AB is equal to BD. Find the position vector of D. So we've been given that AB is equal to BD. So in other words, what they're saying is that the modulus of AB is equal to the modulus of BD. Basically, these two lengths are equal. So what we need to find first is the vector AB. So we can get that from saying OB minus OA. So AB should be equal to, what is OB? Our OB is 520, 520, 520 minus our OA. Our OA is negative 214, negative 214, 14. Alright, so let's simplify that. That's 5 plus 2, which gives us a 7. Then we've got 2 minus 1, which gives us a 1. And then we've got 0 minus 4, And we said what we want is the modulus of AB. So the modulus of AB would be the square root of 7 squared plus 1 squared plus negative 4 squared. So the modulus of AB, or the magnitude of AB, is the square root of 7 squared plus 1 squared plus 4 squared. And that gives us the square root of 66. Root 66. Okay, and now we have to do the same for BD. Right? So we need to find what BD is, the vector BD. So BD, we can get that from saying OD minus OB. And I believe OD is what we are looking for. Yes, we're looking for OD, but we know that our D lies on L2, so we can get the general coordinates of D using the equation of line L2. So from the equation of line L2, we know that any point must have coordinates of the form -2 plus 3 mu, 1 plus mu, and 4 minus 2 mu. So we can say that our OD is equal to that set of coordinates. Is equal to, we said what are the general coordinates for OD? -2 plus 3 mu, -2 plus 3 mu, 1 plus mu, and then 4 minus 2 mu. 4 minus 2 mu. And this is minus OB. What is OB? OB is over here. That's the 520. So that's 520. And this gives us, we've got -7 plus 3 mu. Then we've got -1 plus mu. And then we've got 4 minus 2 mu. These are the coordinates for BD. Now we have to find the magnitude of BD with those coordinates that we have. So the magnitude of BD is the square root of, that's -7 plus 3 mu squared plus -1 plus mu squared plus 4 minus 2 mu squared. Alright, so at the beginning we say that the modulus of AB, or the magnitude of AB, is equal to the magnitude of BD. Okay, so now we've got our two magnitudes. We know that root 66, which is the magnitude of AB, is equal to the magnitude of BD, which is root -7 plus 3 mu squared plus -1 plus mu squared plus 4 minus 2 mu squared. And now let's square both sides to get rid of the square roots. So 66 is equal to -7 plus 3 mu squared plus -1 plus mu squared plus 4 minus 2 mu squared. And now let's expand all these brackets. So we get 9 mu squared minus 14 times 3, that is minus 42, minus 42 mu, and then we've got 7 squared, so that's positive 49, plus mu squared minus 2 mu plus 1 plus 4 mu squared minus 16 mu plus 16. Alright, so let's simplify, see if we've got like terms. 9 mu squared plus mu squared, which is 10 mu squared, plus 4 mu squared, that's 14 mu squared. 14 mu squared negative 42 mu, negative 2 mu, that's negative 44 mu, and negative 16 mu, so that gives us negative 60 mu. Then we've got 49 plus 1, which is 50, plus 16, which is 66. So that's plus 66. Alright, so I'm just going to write this on the side. 66 is equal to 14 mu squared minus 60 mu plus 66. Alright, so let's put everything on one side. So that's 14 mu squared minus 60 mu plus 66 minus 66 equals 0. 14 mu squared minus 60 mu is equal to 0. So we can factor out 2 mu, and in the bracket we've got that 7 mu minus 30, and this is equal to 0. So mu is either 0, or we've got 7 mu minus 30 is equal to 0. So that means 7 mu is equal to 30, and mu is equal to 30 over 7. Alright, so we know that our mu must be the 30 over 7, because if we have mu is 0, going back to the equation of line L2 here, then that just means we're focused on the point negative 2, 1, 4. Alright, so our mu is 30 over 7. Now that we know what mu is, we can find what OD is. We say that the general coordinates of OD are negative 2 plus 3 mu, 1 plus mu, 4 minus 2 mu. So now we can substitute our value for mu. So that's negative plus 3 times 30 over 7. Then we've got 1 plus 30 over 7. We've got 4 minus 2 times 30 over 7. Alright, let's close the brackets, and now let's simplify. So that's negative 2 plus 3 times 30 over 7, which gives us 76 over 7. We've got 1 plus 30 over 7, which gives us 37 over 7. And finally, we've got 4 minus 2 times 30 over 7, and this gives us negative 32 over 7. And this here is the position vector of D. Number 9. The complex numbers z and omega are defined by z is equal to 1 minus I and omega is equal to negative 3 plus 3 root 3I. Part A. Express z omega in the form a plus bi, where a and b are real and in exact surd form. Alright, so we need to find what z omega is. So we're multiplying z, which is 1 minus I, with omega, which is negative 3 plus 3 root 3I. Okay, so we are going to get, that's 1 times negative 3, that gives us a negative 3. Then we've got negative I times 3 root 3I, so that's negative 3 root 3I squared. And then we've got our 1 times 3 root 3I, so that gives us 3 root 3I. And we've got negative I times negative 3, so that's a positive 3I. Okay, so z omega is equal to, that we're going to use here the idea that I squared is equal to negative 1. So this I squared here will be replaced with a negative 1. So we've got negative 3 plus 3 root 3. And then for the second part, I'm just going to factor the I out. So this becomes plus 3 root 3 plus 3I. So this part is the real part, and that's the A, and then this part is the imaginary part, the BI. Okay, and this is our final answer. Part B, express z and omega in the form rei theta, where r is greater than 0 and theta is between negative pi and pi. Give the exact values of r and theta. Alright, so let's start with z. Z is equal to 1 minus I. We know that r is equal to the modulus. So the modulus of z is equal to the square root of 1 squared plus negative 1 squared, which would be root 2. And then next we need to find the value for theta. So I'll do it on the side here. Let's draw a complex plane. This here is the imaginary axis, and then we've got our real axis. So let's say, so our complex number is 1 minus I, so let's say 1 is there on the real axis and negative I would be here on the imaginary axis, so our complex number would be here, and we need to find its argument. So let's draw a line to our complex number, and the argument is the angle that it forms with the positive real axis. So this is the theta, that's the argument we are looking for. So we can actually just complete this triangle. This is a right angled triangle, and we know that this here is 1 and this is also 1 since that's negative I. So we know that our theta is equal to, that's arctan of the opposite is 1 and the adjacent is 1, so theta must be equal to 1/4 pi. But notice how the angle that we're forming is below the real axis, so it means that that angle is negative, right? So theta must be negative arctan of 1, which is negative 1/4 pi. So here we can say that therefore z is equal to, its r is root 2, ei, and theta is negative 1/4 pi, right? And we're going to do the same for omega. We know that our omega is equal to, that's negative 3 plus 3 root 3i. So let's start by finding its modulus. So that is the square root of negative 3 squared plus 3 root 3 squared. So the modulus for omega is equal to, let's punch this into the calculator, that is the square root of negative 3 squared plus 3 root 3 squared. This gives us a 6. Alright, and now we need to find the argument for omega. Again, let's sketch our problem. So we've got our complex plane here. So this here is the real axis, and this here is our imaginary axis. Right, so our complex number is negative 3. So 1, 2, 3, we'll say negative 3 is somewhere here, and then 3 root 3i. So let's say 3 root 3i is somewhere here, 3 root 3i. It means our complex number would be here. Let's draw a line going to our complex number. And the angle that we're looking for is this angle over here, the angle that it forms with a positive real axis. And the way that we're going to find it is to draw this triangle over here and start by finding the angle that's inside the triangle. We'll call this angle here angle alpha. Alright, and so we know that this distance from here to here must be equal to 3, and then we know that the height is 3 root 3. This is a right angled triangle, so we know that our alpha must be equal to arctan of, that's the opposite over the adjacent, so arctan of 3 over 3 root 3. So alpha is equal to, let's punch this into the calculator, that's arctan of 1 over root 3, and that gives us 1 over 6 pi. 1 over 6 pi. But remember, what we're looking for is this blue angle that we have over here. So it means we have to add the 90 degrees to alpha to get the blue angle that we're looking for. So that becomes 1 over 6 pi plus 90 degrees in radians is 1 over 2 pi, which gives us, that's 1 over 6 plus 1 over 2, that gives us 2 over 3 pi. 2 over 3 pi. That's the argument for omega. Alright, so let's just go back to blue and conclude that omega is equal to, its modulus is 6, 6EI, and the angle is 2 over 3 pi. And that's our final answer. Part C. On an Argand diagram, the points representing omega and z omega are A, B, and B respectively. Prove that OAB is an isosceles right-angled triangle where O is the origin. Alright, so let's draw our complex plane. So this here is our imaginary axis, and then we've got our real axis. So let's start with A. A would be our omega. So what is omega? Omega is equal to, I want it in the form A plus BI. So that's negative 3 plus 3 root, negative 3 plus 3 root 3I. And we also want our Z omega, which is this long one over here. Let me just copy that as well. So Z omega is equal to negative 3 plus 3 root 3 plus 3 root 3 plus 3I. Okay, so let's start with omega. Our origin is here. We want omega. Omega is negative 3. So negative 3, let's put it somewhere here. Negative 3, and then 3 root 3I, that is 5 something, 5 point something. So 3 root 3, I'll say that's somewhere here. Try to be as accurate as you can, right? And so this here would be our point A. And now we need point B, which is Z omega. So Z omega is negative 3 plus 3 root 3. Negative 3 plus 3 root 3 is approximately 2.19. So that is, I'll put it somewhere here. That is negative 3 plus 3 root 3. And then we've got 3 root 3 plus 3. So what would that be? That is 8.19. So 8.19 should be somewhere here. That's 3 root 3 plus 3. Okay, so it must mean our point B, in fact, let me just erase that or write it on the other side. So this is 3 root 3 plus 3. And our point would be over here. And so let's join the points to form our triangle from A to O, and then from O all the way to B. And our right angle should be over there, but my diagram is quite poor, so that's why it's a bit off. Anyways, we know that the modulus of A is the modulus of omega. The modulus of omega is 6. So this distance from O to A is 6. And then we also know that I should have labeled this as B. And so the first step is to prove that this is isosceles, right? So to prove that this is isosceles, it means that the distance from OA should be equal to the distance from A to B, right? A to B. OB would be our hypotenuse. So we say that OA is 6, right? So now we need to find what AB is. So let's find the modulus of AB. So the modulus of AB would be equal to the square root of what are our x coordinates or our real coordinates. So for A, that's minus 3 minus the x coordinate at B, which is minus 3 plus 3 root 3, right? And this is squared. I'm just using the formula for length of a line plus the y coordinates, or the imaginary coordinates in this case. So for A, that is 3 root 3. I should extend that. And this is minus the 3 root 3 plus 3 there. 3 root 3 plus 3. Okay, so let's just simplify first. So that is, in the first bracket, the negative 3 and this negative 3 will end up cancelling. So we end up with a negative 3 root 3 squared, plus in the second bracket 3 root 3 and the 3 root 3 here will end up cancelling. So we end up with plus 3, this should be squared, plus 3 squared. Okay, so if we simplify this, punch this into the calculator, this is the square root of, that is negative 3 root 3 squared plus 3 squared, and that gives us a 6, right? So this means that AB is also equal to 6, so therefore OA is equal to AB, and that means that this triangle is indeed isosceles. Now the second part is that they are saying that this triangle is right angled, so we also need to prove that. So now that we know that this triangle is isosceles, it must mean that its base angles, this angle and this angle, I'll call them alpha. These two angles must be equal since this triangle is isosceles. So these must be the base angles. So let's find what alpha is. We can find alpha by saying alpha is this angle minus that angle. So we're saying that our big angle here is the same as the argument of A. We said A is omega. So we're saying that that's argument of omega minus the smaller angle here. The smaller angle would be the argument of B. The argument of B is Z omega. So that's arg Z omega. Now instead of carrying out this calculation exactly as it is, we know that there is a rule that tells us that arg Z omega is equal to arg Z plus arg omega, right? So in this case we've got arg omega minus arg Z omega, so that would be the same as making negative arg Z the subject of the formula. So bringing arg Z to this side, so it becomes negative arg Z is equal to arg omega minus arg Z omega, and this here is exactly what we have over here. So we're saying this is equal to negative arg Z. So all we have to do is to find the negative argument of Z, and I believe we've found the argument of Z already. We know that the argument of Z is negative 1/4 pi from part B. So we're saying that negative arg Z must be equal to negative 1/4 pi. So negative arg Z is equal to 1/4 pi. And so what that means is that our angle alpha is 1/4 pi, right? And this angle alpha is also 1/4 pi. And so that means angle OAB must be equal to we know that angles in a triangle must add up to 180 degrees, or if we're in radians, they must add up to pi. So angle OAB must be pi minus 2 times a quarter pi, right? So that's pi minus half. So OAB must be equal to 1 over 2 pi, which is 90 degrees, making this triangle a right-angled triangle. So we have proved both cases, that it is isosceles and that it is right-angled. Part D says, using your answers to part B, prove that tan 5 over 12 pi is equal to root 3 plus 1 over root 3 minus 1. Okay, so let's look at part B. From part B, what information do we have? It looks like we're going to need the argument of z and the argument of omega. So I'm just going to put those on the side and we'll get back to them. So the argument of z is negative 1 over 4 pi, and the argument of omega, what is the argument of omega, is 2 over 3 pi. 2 over 3 pi. Now what's going on here with what they want us to prove? Root 3 plus 1 over root 3 minus 1. This looks like it's coming from z omega, because if you factor out a 3 in z omega here, you end up with root 3 plus 1. If you factor out a 3 here, you end up with root 3 minus 1. So this must have something to do with z omega. So let's just write our z omega down here. Z omega, we said, is, I'll actually write this as 3 root 3 minus 3 for the sake of this. So that's 3 root 3 minus 3 plus 3 root 3 plus 3i. So given that we're saying that this looks like it's coming from z omega, since this is tan 5 over 12 pi, this must mean we're looking at the argument of z omega. So if we're to draw this on a complex plane, we've got our imaginary axis here, and then we've got our real axis, right? So we've got 3 root 3 minus 3, let's put that here, 3 root 3 minus 3, and then we've got 3 root 3 plus 3. 3 root 3, in fact, let me write it on the other side. That's 3 root 3 plus 3. That's that point. So our complex number is over there. And let's draw a line from the origin to our complex number. Alright, and now we want to find the argument of our complex number, z omega. So this length going upwards, that is 3 root 3 plus 3, and then we know that this distance going across is 3 root 3 minus 3, and this is our argument, and that's the argument of z omega. So we're saying the argument of z omega is equal to arctan of the opposite, which is 3 root 3 plus 3, over the adjacent, which is 3 root 3 minus 3. Okay, so let's simplify that a bit. So arg z omega is equal to arctan of, we can factor out a 3 in both the numerator and the denominator, and so we end up with 3 root 3 plus, that should be 1, and this is all over 3 root 3 minus 1. And so these 3's cancel out, and so arg z omega is equal to arctan of, that is root 3 plus 1 over root 3 minus 1. And so we can apply tan on both sides, so that this becomes tan of arg z omega is equal to our root 3 plus 1 over root 3 minus 1. So we've got the right hand side. Now we just need to figure out how to get the left hand side. So on the left hand side so far we've got tan arg z omega. Right, so I'm just going to bring what we have here. Tan arg z omega, and this is equal to root 3 plus 1 over root 3 minus 1. Right, so we need to find arg z omega, and in part C we said that arg z omega is equal to arg z plus arg omega. So we're going to use that idea again. Arg z omega is equal to arg z plus arg omega. This is where those results from part B come into play. So we know that arg z is negative a quarter pi. So arg z omega is equal to negative a quarter pi plus arg omega, which is 2/3 pi. So plus 2 over 3 pi. So arg z omega is equal to, let's punch that into the calculator, that's negative 1 over 4 plus 2 over 3 pi, and that gives us 5 over 12 pi. 5 over 12 pi. So we can replace this arg z omega with 5 over 12 pi and conclude that therefore tan 5 over 12 pi is in fact equal to root 3 plus 1 over root 3 minus 1. Number 10, part A. By writing y equals sec cubed theta as 1 over cos cubed theta, show that dy d theta is equal to 3 sine theta sec 4 theta. Alright, so we're given that y is 1 over cos cubed theta, and we need to find dy d theta. So this is a quotient and we need to differentiate that quotient. So dy d theta is equal to, we can write that as y is equal to u over v, and we know that the result that we want is dy dx is equal to v du dx minus u dv dx, and this is all over v squared. So we're saying u is our numerator, which is this 1 over there, and then v is our denominator, which is the cos cubed theta. I'll write it as cos theta cubed. Alright, so we need to find what du dx is. So if you differentiate a constant, you get a 0, and then we need to find what dv dx is. So you bring down your power, so that's 3 cos, subtract 1 from the power, so cos squared theta. Differentiate the inner function, you get a negative sine theta. So dv dx is equal to, that's negative 3 sine theta cos squared theta. Alright, yeah, this should be dy, this should be with respect to theta, not with respect to x, my bad. So everywhere where we've got a dx here, that should be d theta, and so this is d theta. Alright, so now let's write it over here. So we want v du, v du would be cos theta cubed times 0, so that gives us a 0 minus u dv, so that's 1 times negative 3 sine theta cos squared theta, so that's negative 3 sine theta cos squared theta, and we are dividing by v squared. V squared would be our cos theta cubed squared, which is cos to the 6th theta. Alright, so let's simplify what we have here. Dy d theta is equal to negative becomes a positive, so 3 sine theta cos squared theta over, that's cos to the 6th theta. So that cos squared theta gets cancelled out, and let's subtract 2 from here. We end up with cos to the 4 theta. So we know that our dy d theta is equal to 3 sine theta times 1 over cos to the 4 theta, which we know that we can write as sec to the 4 theta. So dy d theta is equal to 3 sine theta sec 4 theta, and that's our final answer. Part B, the variables x and theta satisfy the differential equation x squared plus 9 sine theta d theta dx is equal to x plus 3 times cos to the 4 theta. It is given that x equals 3 when theta is 1 over 3 pi. Solve the differential equation to find the value of cos theta when x is 0. Give your answer correct to 3 significant figures. So let's start by separating our variables. On the left hand side, we're going to have sine theta over cos to the 4 theta, or moving this cos to the 4 theta to the left, and this is with respect to theta. Then everything that has x is going to the right hand side, so we end up with x plus 3 over x squared plus 9, and this is with respect to x. So we know that we can write the left hand side as sine theta sec to the 4 theta d theta, and this is equal to, that's x plus 3 over x squared plus 9 with respect to x. Now for the left hand side, we've got sine theta sec to the 4 theta. If we've got 3 sine theta sec to the 4 theta, it must integrate to give us sec cubed theta. But the only problem is that we are missing a 3. So to create that 3, we're going to multiply both sides by 3. Okay, so we know that the left hand side now integrates to give us sec cubed theta. Alright, so now we need to play around with the right hand side. I'm going to do that on the side. So I've got 3x plus 3 over x squared plus 9. This can be written as 3x plus 9 over x squared plus 9. I'm going to distribute the denominator, so that's 3x over x squared plus 9 over x squared plus 9. We can integrate these two functions, so that's good. We can go back to our equation here. We've got 3 sine theta sec to the 4 theta with respect to theta, and this is equal to 3x over x squared plus 9 over x squared. In this case, I'm actually going to write it as 3 squared, which I'll explain in a bit. This is with respect to x, and now we want to integrate both sides. We said our left hand side, 3 sine theta sec to the 4 theta, should integrate to sec cubed theta, as we proved in part A. So that means on the left we've got sec cubed theta plus a constant of integration, and this is equal to, here we want to integrate 3x over x squared plus 9. We're going to use the method of recognition here, which is basically the idea that if you've got a derivative on the numerator and the function is on the denominator, and you've got a constant outside the integral sign, it means that your integral should be k ln f of x. Alright, so that's the idea we want to use over here. So what I'm going to do is write this as x squared plus 9 with respect to x. If you differentiate the denominator, you get 2x, right? But on our original numerator, we've got a 3. That's the only difference. So I'm going to put a 3 over 2 outside the integral sign, because if we say 3 over 2 multiplied by 2x, these 2's cancel out and we get our original numerator of 3x. The reason I've done this is so that we have this in the form k f prime of x over f of x with respect to x, because if you differentiate x squared plus 9 you get 2x, right? But we need to maintain our original numerator of 3x, so we're going to multiply by a constant outside of the integral sign. So this means this here would actually integrate to give us 3 over 2 ln f of x. From here f of x is the denominator, so ln x squared plus 9. Alright, so it means what we have here is 3 over 2 ln x squared plus 9. Then for this part over here, that is 9 over x squared plus 3 squared. We're going to use the idea that the integral of 1 over x squared plus a squared with respect to x is equal to 1 over a arctan of x over a. Alright, so we can actually just take the 9 that we have here outside the integral, so that's 9, and then this is 1, this is with respect to x. So what we end up with is 9 over, what is our a? Our a is 3, and this is arctan of x over a, which is 3. So this is 3 arctan of x over 3. Alright, so coming back here, this will be plus 3 arctan x over 3. Okay, so this is our general solution. Now we need to evaluate c. So we are told that x is 3 when theta is a third pi, so we can use that information. X is 3 when theta is a third pi. So sec cubed theta is 1 over cos cubed theta, and we are told that theta is a third pi plus c is equal to 3 over 2 ln, what is x? X is 3. So that's 3 squared plus 9 plus 3 arctan, that's x, which is, what's x again? I keep forgetting x. X is 3. Alright, so let's evaluate our left hand side. On the left we've got 1 over, that's cos 1 over 3 pi, and this is cubed, so this gives us an 8. So we've got 8 plus c is equal to, then on the right hand side we've got 3 over 2 ln 3 squared plus 9, so that's ln 18, plus 3 arctan of 1, so that's plus 3 over 4 pi. So we can say that c is equal to 3 over 2 ln 18 plus 3 over 4 pi minus 8. So our differential equation gives us the solution sec cubed theta plus 3 over 2 ln 18 plus 3 over 4 pi minus 8 is equal to 3 over 2 ln x squared plus 9 plus 3 arctan of x over 3. Alright, that's a long solution. We also need to find cos theta when x is equal to 0. When x is 0, so let's substitute x with 0. We've got sec cubed theta plus 3 over 2 ln 18 plus 3 over 4 pi minus 8, and this is equal to 3 over 2 ln, this becomes 9 since x is 0, and we've got plus 3 arctan of 0. Arctan of 0 is 0, so we don't need to consider the 3 arctan x over 3. Alright, so let's make sec cubed theta subject of the formula. Sec cubed theta is equal to 3 over 2 ln 9 minus 3 over 2 ln 18 minus 3 over 4 pi plus 8. So sec cubed theta is equal to, I'm just going to combine these two using laws of logarithms. 3 over 2 ln 9 over 18, so that's ln 1 over 2 minus 3 over 4 pi plus 8. And then I'm just going to put both sides to the power 1 over 3 to get rid of this power 3 on the left hand side. 1 over 3. So what we have is that sec theta is equal to 3 over 2 ln half minus 3 over 4 pi plus 8, and this is to the power 1/3. And now we can change sec theta to 1 over cos theta, because what we really want is cos theta. This is equal to 3 over 2 ln half minus 3 over 4 pi plus 8 to the 1/3. And so cos theta is equal to 1 over 3 over 2 ln half minus 3 over 4 pi plus 8 to the power 1 over 3. Do they specify whether they want it in exact form or they want it to 3 significant figures? So we can punch this into the calculator, and this gives us a final answer of 0.601, correct to 3 significant figures. And I believe that is the paper. Alright, that was an interesting paper. I hope you guys found this video useful. If you did, please leave a like and make sure to subscribe for more videos like this. Bye bye.